Energy is the power derived from the utilization of physical or chemical resources, especially to provide light, heat, or to work machines. These can come in many forms and sizes. The unit in which energy is measured is the joule. Energy is a conserved quantity. The law of conservation of energy states that energy can be converted in form but not created or destroyed. Today, let's talk about the scale of energy. The smallest amount of energy isn't zero, as zero energy is impossible to all sorts of quantum effects. The absence of energy is physically impossible. Instead, our starting point will be the energy of a single radiant photon with a frequency of just 1 Hz. It has an energy of only 6.626 times 10 to the negative 34th joules. Photons are most well known as the carrier particles of light, but come at various frequencies and energy. A typical AM radio photon of 1 MHz has an energy of 6.6 times 10 to the negative 28th joules. Photons emitted by the microwave oven have a frequency of 2.45 GHz, which corresponds to about 1.6 yoctojoules, 1.6 times 10 to the negative 24th joules. As we climb up the electromagnetic spectrum, a single infrared photon has an energy of 250 yoctojoules. The average chemical bond between two hydrogen atoms ranges from 7 to 22 septojoules, which is 7,000 yoctojoules. One single neutrino contains up to 45 septojoules of energy, and 160 septojoules are equal to 1 electron volt of energy, carried by a single electron. Photons in visible light range from 300 to 500 septojoules of energy, and ultraviolet photons go to 700 septojoules. At 2 attojoules, or 2 million yoctojoules, is the energy of the average X-ray photon. 3 femtojoules, which is 3 billion yoctojoules, is the energy contained in the average red blood cell, and a single gamma-ray photon can contain over 20 femtojoules of energy. The total rest mass of a single electron is 82 femtojoules. Followed by 34 picojoules, or 34 trillionths of a joule of energy for the total energy released in the nuclear fission of one uranium-235 atom, the most common uranium isotope used in nuclear power plants. The rest mass energy of a proton is about 150.3 picojoules, followed by a neutron at 150.5. The rest mass of a helium nucleus, commonly referred to as an alpha particle, is 600 picojoules, which is roughly equal to the amount of vacuum energy produced by quantum fluctuations over 1 cubic meter of space as measured by the Wilkinson probe. 700 picojoules is the energy needed to lift a grain of sand by 1 millimeter. The mass energy of a W boson is about 13 nanojoules, or 13 billionths of a joule, followed by Z bosons at 15 nanojoules. The massive Higgs boson has a rest mass energy around 20 nanojoules, and 160 nanojoules is the energy required for a mosquito to fly itself 1 meter. 0.11 joules is the energy produced by an American $50 falling 1 meter, and in metric, 1 joule is the amount of energy needed for a force of 1 Newton to move an object 1 meter. It's equal to the energy of 100 grams falling 1 meter, or the energy required to heat 1 gram of dry air by 1 degree centigrade. To heat 1 gram of water by 1 centigrade, 4.1868 joules of energy are required. This is the value of 1 calorie. The most energetic cosmic ray ever detected had 5 joules of energy. It was most likely a single proton traveling only slightly slower than the speed of light. A single proton normally carries 50 joules. A lethal dose of X-rays would have an energy of 300 joules. Also 300 joules is the approximate energy you need to jump as high as you can. 330 joules are needed to melt 1 gram of ice into water. And using a 10-watt flashlight for 10 minutes requires around 600 joules of energy. 1 horsepower equals approximately 750 joules, and the energy required to lift the average human 1 meter is 801 joules. The solar constant is the amount of solar energy received, which is 1.361 kilojoules per square meter per second, and the kinetic energy produced by firing an M16 rifle is 1.8 kilojoules. 2.3 kilojoules is the required energy to vaporize 1 gram of ice into steam. 3.6 kilojoules are equal to 1 watt hour, and 4.2 kilojoules is the approximate energy release upon exploding 1 gram of TNT. This is also the value of 1 food calorie, not to be confused with a metric calorie. The energy contained in an alkaline AA battery is about 9 kilojoules, and the energy released by the metabolism of 1 gram carbohydrates or proteins is 17 kilojoules. 38 kilojoules for the metabolism of 1 gram of fat, and 50 kilojoules for the combustion of 1 gram gasoline. which is roughly equal to the kinetic energy of moving 1 gram at 10 kilometers per second. 500 kilojoules is the energy produced by a 1 gram meteor impacting the Earth. 1.2 megajoules or 1.2 million joules is the approximate food energy of 1 bar of Snickers, 280 food calories, while 3.6 megajoules equals 1 kilowatt hour, commonly used in households. 4.2 megajoules is the energy released by exploding 1 kilogram of TNT, and 8.4 megajoules or 2000 calories is the recommended daily food intake for the average moderately active adult woman, where the recommended food energy intake per day for the moderately active man is about 11 megajoules or 2600 calories. 40 megajoules is the approximate energy received from the combustion of 1 cubic meter of natural gas, and 63 megajoules is the theoretical minimum energy needed to accelerate 1 kilogram to escape velocity. Riding the Tour de France for a 65 kilogram rider at an average of 5 watt per kilogram will require 100 megajoules of energy. 730 megajoules is the approximate amount of energy received from burning 16 kilograms of oil. 1.4 gigajoules or 1.4 billion joules is the theoretical minimum amount of energy required to melt a ton of steel. At 2 gigajoules we have the Planck energy, one of the more weirdly valued Planck units, and 3.3 gigajoules is the approximate average amount of energy expended by the human heart muscle over an 80-year lifetime, and 4.4 gigajoules is the energy released by exploding a ton of TNT, which is roughly the same as the annual energy usage of the standard refrigerator. 5 gigajoules is the average energy in a lightning bolt, and the kinetic energy of an Airbus A380 at cruising speed is 23 gigajoules. 46 gigajoules is the yield energy of the massive ordnance air blast bomb, the second most powerful non-nuclear weapon ever designed. And 73 gigajoules was the energy consumed by the average US automobile in the year 2000, while 86 gigajoules is called a megawatt day, used in the context of power plants. The total energy released in the nuclear fission of 1 gram of uranium is 88 gigajoules, and 240 gigajoules is the approximate food energy consumed by the average human in an 80-year lifetime. 3.4 terajoules, that's 3.4 trillion joules, is the maximum fuel energy of the Airbus A330-300, and blowing up 1 kiloton of TNT releases 4.2 terajoules of energy. 11 terajoules is the energy contained in the jet fuel in a Boeing 747-100B, and just above that, at 12 terajoules is the orbital kinetic energy of the International Space Station. The yield of the little boy atomic bomb dropped on Hiroshima in World War II was 15 kilotons, translating into 63 terajoules of energy. The yield of Fat Man, the atomic bomb dropped on Nagasaki, was larger at 21 kilotons or 88.2 terajoules. Then at 90 terajoules is the theoretical total mass energy of 1 gram of matter. So the energy released by the annihilation of 1 gram antimatter and matter is the double of that, 180 terajoules. The Chelyabinsk meteor, which exploded over Russia in 2013, released 375 terajoules of energy. This is more than the total mass energy of the Eiffel Tower. 600 terajoules of energy is released by the average hurricane per second. A severe thunderstorm can easily top this, reaching up to a petajoule of energy. A petajoule is a quadrillion joules, 15 zeros, but even these absurd amounts of energy will seem small by what's yet to come. It may sound big, but the yearly electricity consumption in Greenland as of 2008 was also 1 petajoule. This means that over 10 Nagasaki nukes would have to be detonated to produce enough energy to keep Greenland going for just 1 year. This may seem a lot, but energy consumption magnitude should really not be underestimated. This is followed by 4.2 petajoule for exploding 1 megaton of TNT, which is roughly the same as the annual energy consumption of the Netherlands. And 10 petajoules is the estimated energy released during the formation of meteor crater in Arizona, just stopping this for the yearly energy consumption in Mongolia at 11 petajoules, and 90 petajoules for the mass energy of a kilogram of matter. 100 petajoules of energy were released on the Earth's surface by the magnitude 9.3 Indian Ocean earthquake of 2004, truly putting the power of the Earth in perspective. The total solar energy that strikes our planet per second is 170 petajoules. The yield of the Tsar Bomba, the most powerful nuclear weapon ever to be detonated at 50 megatons, released 210 quadrillion joules of energy, with the annual energy consumption of Norway in 2008 at 420 petajoules, which about coincides with the approximate energy needed to accelerate 1 ton to 1/10 the speed of light. 800 petajoules was the estimated energy released by the eruption of the Indonesian volcano Krakatoa in 1883. The Krakatoa eruption was one of the most powerful and destructive volcanic eruptions of our era. Its blast wave and explosions were so violently devastating they could be heard on the island of Mauritius on the other side of the Indian Ocean, nearly 5,000 kilometers away. In 2008, the annual energy consumption for Australia was 850 petajoules. This means Australia uses more energy than the most powerful volcanic eruption in recorded history. 1.2 exajoules, that's 1000 petajoule or 1 quintillion joules, is the annual energy consumption of the United Kingdom in 2011, followed by France at 1.7 exajoules, 1.9 for South Korea, Germany at 2.1, India at 3.34, Russia at 3.4, and Japan at 3.56 petajoules per year. 14 exajoules is what the United States consumed in 2009, and 17 exajoules goes for China in 2009, while the energy released in one day by the average hurricane in producing rain is 400 times greater than the wind energy and reaches into 50 exajoules of energy. 64 exajoules was the yearly electricity consumption of the world as of 2008. Total energy consumption of the world in 2010 was 500 exajoules, meaning we humans consume 500 times more energy than the largest volcanic eruption in recorded history. 800 exajoules is the estimated global uranium resources for generating electricity as of 2005. Diving back further in time to 1815, the Tambora volcano in Indonesia, then the Dutch East Indies, erupted. It released a baffling 33 gigatons of TNT of energy, which is equivalent to 1.4 zetajoules or 1.4 sextillion joules. The eruption of Mount Tambora was so devastating to the Earth's climate, the following year skipped its summer. Going up from here, there's about 6.9 zetajoules of energy contained in the world's natural gas reserves as of 2010. At around 8 zetajoules, we place the Toba eruption, which occurred on the Indonesian island of Sumatra about 74,000 years ago. This explosion ranked a full 8 on the volcanic explosivity index and erupted a mind-blowing 3,000 cubic kilometers of stone and ash. Its impact was so devastating, geologists have claimed it nearly caused human extinction, with as little as 3,000 to 10,000 hominids surviving worldwide. An even more dangerous potential eruption could come from the Yellowstone caldera in the western United States, which according to some estimations could produce an eruption releasing up to 15 zetajoules of energy. This would effectively cause an extinction level event on Earth, decimating the North American continent under meters of volcanic ash. For comparison, 15 zetajoules is the approximate solar energy that hits the Earth per day. While these numbers are pretty intense, the universe has a lot more to offer. 24 zetajoules of coal energy still remain inside the Earth as of 2010, and all the remaining fossil fuels on Earth combined translate into 39 zetajoules of energy, which is approximately equal to the total energy released by the magnitude 9.3 2004 Indian Ocean earthquake. 500 zetajoules of energy were released 66 million years ago in the formation of the Chicxulub crater in the Yucatan Peninsula, which killed the dinosaurs. 1 yottajoule or a septillion joules is the largest SI prefix available. It has 24 zeros, and the first relevant energy would be 5.5 yottajoules, which is the annual amount of energy received by the Earth from the Sun. 60 yottajoules is the typical upper limit for energy release in a solar flare. The total energy output of the Sun per second is 380 yottajoules. 1000 yottajoules is the energy released by the impact that created the Caloris basin on Mercury, and the kinetic energy of the Moon in its orbit around the Earth is 38,000 yottajoules. The rotational energy of the Earth itself is 200,000 yottajoules, and 1.8 million yottajoules is the gravitational binding energy of Mercury. The total energy output of the Sun each day is 33 million yottajoules, and the gravitational binding energy of the Earth is 200 million yottajoules, while its kinetic energy in orbit is 2.7 billion yottajoules. 12 billion yottajoules goes for the Sun's yearly energy output, and converting one lunar mass into energy would result in 6.6 quadrillion yottajoules. The gravitational binding energy of the Sun is 227 quadrillion yottajoules, and converting one whole Earth mass into energy would result in 540 quadrillion yottajoules. 50 quintillion yottajoules is the average energy of a gamma ray burst, which falls just short under the energy release in a supernova, which is 100 quintillion yottajoules, which is 1 joule with 44 zeros behind it. The energy released in a supernova is sometimes put into a unit which astronomers refer to as a foe. I'm not kidding, they actually call it a foe, lol. At 11 foes is the brightest observed supernova SN 2015L, followed at 100 foe by the estimated release of energy during a hypernova, when a black hole is born. Hypernovas are amongst the most powerful explosions known to exist, but if you converted a full solar mass of matter into energy, you'd have 1800 foe. The mass energy emitted as gravitational waves during the merger of two black holes, originally about 30 solar mass each, as observed by LIGO, was 5400 foe. The largest gravitational waves observed originated from an 8400 foe merger. GRB 080916C was the most powerful gamma ray burst ever recorded. It had a total apparent energy output estimated at 8800 foe, or 4.9 times the sun's mass energy. 400 trillion foe would result from the visible mass energy of the Milky Way, and converting all the Milky Way's mass energy, including dark matter and dark energy, would result in 1 quadrillion foe, followed up by the total mass energy of the Virgo supercluster, including dark matter. The supercluster in which the Milky Way is situated contains 1 quintillion foe of energy. And finally, the total mass energy of the observable universe is 4.2 times 10 to the 69th joules of energy, a truly energizing number. The only topping to this would be the energy released by the Big Bang, but we can't really know how much that was. This has been a scaling for energy, and I hope I was able to give you some insight into the scale of energy. If you wish to see more scaling like these, consider joining my Discord or donating to my Patreon to help me keep these videos coming. Do you know any relevant energy mentions I haven't mentioned? Let me know in the comments. And as usual, this has been YG Science, and thank you for watching.